The text is now introducing the idea of formal charge. And it's kind of odd, I think, because you can throw out the window octet rule. You can throw out the window CNOS. All those rules are gone. All we obey is formal charge. And so what it ends up being is you end up assigning a number for every single atom in a molecule. Now take a look at this. Here's two Lewis dot structures, but notice how they're different. Right? One has a double bond over. Which one's right? Formal charge tells you. And so next to each atom in that molecule is a number, and that's a formal charge. They're all zeros, and we're going to find out, oh, that's the best you can do. So, but each of those numbers has to be calculated. So in the end, it really isn't a bad idea to calculate, CNOS, octet rule. It's not a bad idea because it's going to get you to the right answer a heck of a lot faster. Okay? Because more than likely, if you follow all those rules that we've been talking about, you'll get here faster. So you don't have to be calculating all these formal charges. But we could have started from the very beginning with just formal charges. But I think it would have been frustrating because you had to calculate all these numbers for every stupid little structure you draw. So it's not bad. So we're going to do everything we've done before to try to arrive at the best answers here. So the one with the lowest, with all zeros, is the lowest energy, right? And lowest energy is the best answer. Okay. And that's where we're headed. So let's try one of these. Use formal charges to select the best Lewis structure for phosphoric acid. Okay. Now let's start out here. Let's see. We have how many hydrogens? We've got 3. We'll count up the valence. Phosphorus has 5, right? And how many oxygens do I have there, Gilbert? 4 of them, and each has 6, right? So is there any charge, Kimberly? No, so I don't add to the total or subtract. There's no charge. So 3 times 1 is 3, plus 5 is 8, and 24. We got 32 valence electrons. Okay, and follow all the rules we did before. I like to connect everything, make octets, anything left over, put on the center atom. So let's connect everything. Make octets on everything that's surrounding. And see if we can get lucky and be done. Maybe I used them all up, maybe I didn't, so now's the time to check. Anything left over, put on the center atom. So let's see here. This oxygen, 2, 4, 6, 8. And notice they're identical, these 4. Right? So you don't have to keep counting. I've got 3 of those oxygens are identical. 3 times 8 is 24. So I used up 24 already. And then this oxygen, he's got 6 lone pairs and a bond. That's 8 more. So I've got 32. I used them all up. Nice and good. And it looks like everything is obeying the octet rule. So we would move on. But is it the best structure? So now this is where things are changing a little bit. We need to know this equation. How do you calculate formal charge? Right? You take the number of valence minus the number of bonds and then subtract off the number of lone electrons. Do that for every single atom in the molecule. Right? So let's, like H. Number of valence of H is just 1. And how many bonds, Lauren, does let's just look at this H right here. How many bonds does it have with it? Just 1. And how many lone electrons are around that, Monica? 0. So valence minus bonds minus lone electrons. So I get 0. Awesome. And all of these hydrogens are the same, right? So I can just write 0 on all of them. Okay. How about these oxygens? Let's check out this oxygen right here. Okay, that oxygen is going to be number of valence is 6 minus the number of bonds. Victoria, how many bonds on that oxygen? On this one right here. 2 bonds. And the number of lone electrons, Kimberly, is 4. 6 minus 2 is 4, minus 4 is 0. Ooh, man, maybe we can get lucky here, right? Now notice that these oxygens are all the same. So we're almost done. Right, we can clean this up a little bit. We're almost done. Okay. So we just have a couple left. Let's check out, do green or something. Let's check out this oxygen, the green one. Number of valence, 6. Number of bonds, Gilbert, with the green oxygen, just 1. Number of lone electrons, everybody, 6. Now we have a number, right? We've got a -1. So this guy's -1. How about the phosphorus? Phosphorus has number of valence, 5. Number of bonds, everybody, 4. Number of lone electrons, 0. +1. So this phosphorus, +1. Okay. Now let's take a look at the rules here. Always choose the Lewis structure with everything zeros. That's the best. Okay? But you can't always get zeros all the time. We'll see why. The sum of all the formal charges equals the overall charge. If it doesn't, you screwed up if it didn't. Right? So what does that mean? Add up all of these formal charges of everything. Let's back up. What's the charge on this? 0. So I better add up all those hydrogens, that phosphorus, and those 4 oxygens. I better add up all those formal charges, and I better get, Frankie, 0. Yeah, because that's the overall charge. And I do, right? In this case, I do get 0. Okay, but I don't have all zeros. A negative formal charge. So I guess if you can't get all zeros, if you can't get all zeros, then you better make sure that negative formal charge is on the most electronegative atom. And Monica, what was the most electronegative element in the world here? F. So whoever's closer to F is the most electronegative. Okay, we got to try to fix this. Let's redraw our structure here. See if we can improve it. Redraw our structure here. Okay, and what do we have? We had them all connected. We had octets on everything. Okay, that's where we were at. So since the guys who have zeros, don't mess with them. Leave them alone. So we just have to mess with the 2 that don't have 0 formal charge. That oxygen and that phosphorus. So probably just do what? Yeah, move one of those, make a double bond. Now what do we have for formal charge? Right? That oxygen is 6 valence minus 2 bonds minus 4 lone electrons, 0. Nailed it. This phosphorus, 5 valence minus 5 bonds, right? Aren't there 5 bonds on that phosphorus now? No lone electrons, 0. They're all zeros. This is the best structure right here. Okay. So let's jump down to, does that make sense so far? Victoria, that makes sense? Okay. We're not going to do this yet. We're going to do it after we talk about bond energies, but would you get all zeros for bromate? Lauren, would you get all zeros for bromate? No. In fact, all the formal charges better add up to be -1. And that -1 formal charge, so it would be the best answer you could get. The best possible answer would be all zeros for formal charges. All zeros, but a single -1 on the, or on a, what atom? That would be the best possible answer, if you can get it. Have a -1 formal charge on an O, because O is, which one's more electronegative? Oxygen is. So the best possible answer you can get, if you can get there, is zeros on everything, but on a single oxygen, have a -1 formal charge. So that's the game. That's the game we're playing. But before we get there, they want us to talk about one little topic. It's kind of off. I think they just slammed it in there, and it's one way that they use to predict synthesizing. This is a more straightforward case, but what energy is involved in making molecules and compounds? Is it even possible? And so one way you can do, like, here's a reaction, and all we want to do is, hey, what's delta H for this reaction? All right, make it a thermochemical equation. What's the enthalpy? Is it endothermic, exothermic, that sort of thing? And they're just saying that you can find delta H by adding up all the bonds that you have to break, add up all the bonds that you have to form, and just subtract the two. Okay? And I see two ways of going about this. One is to actually identify the bonds you got to break. Right? You got to bust these up because they're reactants. Here you got to form because they're products. So if you didn't have a calculator, you'd probably want to just identify the ones you're going to break, right? Like, which bond would you have to break? Victoria, what would you have to break here? Yeah, that C double bond C, you're going to have to break it. Is there anything else you'd have to break? Yeah, this H-H you're going to have to break. Then what are you going to have to form? Yeah, how many CH bonds are you going to have to form? 2 of them. Looks like that might be it. So you can go that route, but I prefer, and there's no problem. You want to do that, you identify what you need to break, what you need to form up. All I'm saying is I get frustrated with this because I often miss a single bond somewhere. I didn't see it. So I just break everything, and I form everything, and I move on to the next one. So since you have a calculator, it's insurance. So that's how I suggest doing it, and that's how I'm going to do it here. So if I break up everything, why not, right? And then form everything. And I'm kind of wasting my time because, like, the CHs, right, they didn't change. So, but they'll just subtract out. It's fine. At least this way I won't miss any bonds because I think the homework is going to get more complicated. Right? There's going to be a lot of stuff in there. So why dig out and see just what's forming, what's breaking? So how many? Let's start out with the CH bonds. How many are there? Kimberly, how many are there? I'm going to bust all this up. How many there's 4. So 4 CH bonds. Now each CH bond, according to this table, Frankie, has an energy of what? CH? Yeah, CH. Perfect. See how we read the table? CH. Combine the C, the H, 411. So 4 times 411 plus, what other bonds I'm going to break? I'm going to break that C double bond C. Victoria, that'd be how much energy? The C 602. Very good. So that's the C double bond C. And I got to break, what, the HH? Gilbert, that's how much energy? This is really HH, right? This is 432. Okay. Now I'll subtract out everything I'm going to form. How many CH bonds, Lauren? 6. Good. And we said that was 411. And what else do I need to form there, Monica? The C-C, which is how much? Yeah, good. 346. Oh, hold it. Is that everything? It's everything, right? Okay. Let's see what I get here. 4 times 411 plus 602 plus 432 minus 6 times 411 minus 346, negative 134. And I can look at the table and for the units. Do you see the units? Right up here. Kilojoules per mole. So that is a what reaction, Lauren? Endothermic or exothermic? Exo. It's giving off heat. So it should happen. It should be spontaneous. Okay, so that's the two parts that you're going to see in the homework. But the meat of it is really this stuff. Okay. Oh, let's catch something because this might be in the homework. What if, Gilbert, there was a 3 in front of this? How many CH bonds would you now have? 12. Exactly. Because now you got 3 of the molecules, so you just pretty much multiply by 3, right? And you have to do that for everything. Pretty much just multiply through by 3. Okay. So let's go to the boards and see if we can knock this stuff out. Help each other out. So do everything you did before. Follow CNOS, follow octet rules, do all that. But calculate formal charges. And notice there's only one compound up here that has a charge. So your best answer for A, C, D, and E is going to be zeros for formal charges for everything. You get that? Hey, you can move on. Okay, let's try it. Yeah, well, we'll start with A. Let's start with A. Yeah, start with A, sorry. Start with A. Get the total valence. Take octets and everything surrounding, anything left over, put on the center, and see if you get lucky. Or not 3 times 7, it'd be 2 times 7, right? And then each sulfur is 6 and oxygen is 6. I think most everybody's getting 26, right, for your valence. Good. So keep going. Okay. Yeah. Okay, great. Now see if everything has a formal charge of 0. And remember the formal charge equation. You're going to have to know it. Formal charge equation was number of valence electrons minus number of bonds minus number of lone electrons. So calculate a formal charge on everything and see if you can get zeros. Well, hang on. Do you have 26?
I think I have 24.
2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Yeah, you need, yeah, so start here, right? Right, you have octets and everything. You have 24. You have to put them there. Now you start making double bonds. Otherwise, you lose track. So don't start throwing double bonds in right away. Right, make octets, everything surrounding. Anything left over, we put on the center atom. I've got 2 left over. So if you haven't figured it out yet, that should be your starting point. Right? And there's going to be definite improvements. Right? There'll be definite improvements. Well, Gilbert, you forgot, right? This is good, and then you erase this. You made a double bond. You just forgot to keep his lone pair up there, right? You can't lose him. You erase this and put it there, right?
Yeah.
Well, don't forget about you have a lone pair up here. You got to keep it up there. Oh, you didn't write in your lone pairs.
Yeah, I tried to do a shortcut.
You got to. Otherwise, you lose track, right? Because this shows you.
Right?
That'll be a 2. So you can't. No shortcuts. Ends up spending more time. Yeah. So he's a -1, he's a +1. Now, everything equals 0. It's good. But since it's neutral, see if you can get all zeros. And it doesn't look bad because the negative is on the most electronegative. Because O is more electronegative than S. But see if you can get all zeros. Right? Boom, boom. See if you make a double bond and see what it does. I think, looks like everyone's pretty much got this one. You ended up making a double bond. So for A, you can get all zeros. Right? Did you get it? So F's are 0, so don't mess with them. This guy's a +1. He's a -1. Right. Oh, you got it. Oh, you got a +1. That's good. So +1 and -1 is 0. So you have zeros for everything. Sorry, you don't have 0. You have 0 total. So see if you can get zeros for everything. Right? Pretty much all you can do is do that. Because don't mess with the F's because they're zeros. -4. There you got 0. Do this and check the S. I bet that's 0 too now. Sulfur 6. Yeah, it's fluorine is 7.
Yeah.
Don't.
It's the sun.
Yeah. Minus the number of bonds. 1, 2, 3, 4. Yeah, you got it. There you got it. Okay. For B, no. A, yeah. A, your best answer is all zeros. Just like you got it. Perfect. Keep going. figure it out. Do B first. That's what I want to be on. Okay, so count up. Do you have 26 on there? You have to have 26. Yeah, so you end up having an extra one. 26. So count up the valence. I mean, sorry, do formal charges and see what you need to mess with. Oh, that's what you're doing? Yeah, so bromine would be 7 minus 3 minus 2. Yeah. Yep. Your starting point would have, my starting point has a lone pair on the bromine, which I think most of you have. You have to have a lone pair on that bromine because you only have 24 electrons. Now you've got 26.
Oh, yeah.
So you need a lone pair on the bromine to get 26 electrons. Because you've got 8 and 8 is 16 and 8 is 24. You need a lone pair here.
Is it 26?
Because you have to add one. It's BrO3 minus.
Oh, all right. I subtracted.
Plus would be short one.
Yeah, I subtracted.
Okay. Now the total works out because you've got a -3 and a +2.
Okay.
So it works out
Yeah.
to be a -1, and that's what you want. But if you can have all zeros and just one -1, that's an even better answer. It's a lower energy. And what's more electronegative, O or Br?
Oh.
O. So the best answer would be zeros on everything but one oxygen. Have it be a negative.
Okay.
And remember how to get zeros for that oxygen. Go back to the last answer. Look at this guy. Oxygen likes it this way. So that's kind of a hint. Okay.
So one of them's gonna have a negative one?
One of them's going to have, okay, now if you do it this, you see you have one double bond. So now you have a negative and a negative. And now this guy, bromine is what? Well, oxygens, these aren't zeros. Oh, that's a double bond? Is that that's a double bond? Oh, okay, yeah, okay, that's good. You got it. Yeah. Oh, yeah, I thought it was a single bond. Yeah, you got it. All right, so these are all negatives, and this is a +2. So +2 and a -3 is a -1, and that's what it's supposed to be. But if you can get all zeros and just one -1, that's even lower energy. And that -1 should be on an oxygen because it's more electronegative. So if you go back to the last question, look how oxygen, if he has a double bond and two lone pairs, he's 0. So if you could do that for 2 of these, do that for 2 of them, and leave one alone. I bet you it'll work. MClO. It's just NClO. This isn't there.
Oh, okay. That's pretty bottom.
Oh, this isn't there. That's not there. It's just NClO.
Oh.
So did you get the bromate B? You should have 2 double bonds. At least it seems like this one works. 2 double bonds and 1 single. Does that one work? Because if you do it this way, 2, 4, then these guys are all zeros. And the -1 is on the bromine. But what's more electronegative? Oxygen is. So this works, but it's not as low of energy as having as having that negative on the oxygen. That's the only thing wrong with it. There you go. For this one, you want to get zeros on everything. Your best answer is zeros on everything and only 1 -1 charge, formal charge. And what's more, and that -1 charge should be on the most electronegative element. So what's the most electronegative? O. So your best answer, see here you have a negative here and a negative here. So make another double bond. Make another one. And then you just end up with 1 negative. Yeah, now you end up with just 1 negative. And bromine, if you calculate him, he's 0. That's the lowest energy.
So whatever does that
All the formal charges have to add up to be it.
Okay.
Anybody figure out a possible answer for C? I think there's 2 ways to get all zeros on C. One way someone found out was with a triple bond.
So I tried to put the octet on everything.
Well, you need 18. You need 18 electrons first. There you go. Okay. So. Yeah. So he's way off. Okay. So what you could do, and one thing you know, oxygen likes double bond. That makes him 0.
Right.
So right away, just move him in.
Okay.
Try that. So that's one thing. And then this guy, you know, is messed up. So just try that.
Okay.
And then now this would maybe be a better shot. Did this one work? Woohoo! Let's make sure we got 2, 4, 6, 8, 10, 12, 14, 16. Ooh, there's 1. Victoria found one answer. Here's one possibility. I'll put it on there. See if you can find the other answer. All right, that's one possibility. Yeah, good. And there's one more possible answer for C, but don't worry about it. If you got one of them, just go on to the next one. But yeah. Yeah, Gilbert. If you got it, you can just go on to the next one. Don't worry about the second answer.
I have 20.
You can only have 18 electrons total.
Okay, so I just do that, right?
Yeah, you got 8, 10, 12, 14, 16. Yeah, there's 18. And now you got to work with the valence, the formal charges, just get everything to be 0. You got all zeros? 2, 4, 6,
Oh,
8,
no.
10, 12, 14, 16, 18. 7 minus 4. He works. I think that, does this work? 5 minus 4 minus 1, 6. Yeah, that works, doesn't it?
Oh, yeah.
This works. 2 lone pairs on that nitrogen. Right?
Yeah.
No, you had it. That was right. Remember this one. Yeah, you got it. It works. There's another one. There's another one. Okay, we're out of time, but I think you got the idea, right, for the homework.